Welcome, ladies and gentlemen, to Edu-ca-te. Today we're going to be talking about the collision theory in rates of reactions. So let us first start with the basics of rates of reactions. So when we're talking about the rates of reaction, what are we actually talking about? So in basic terms, the rate of reaction is just the speed at which the reaction occurs. So it is just the speed at which the products are formed, or it is the speed at which the reactants are used up. So you can see that from this schematic diagram which I've used here, we have got two reactants mixing up to make some product here. So the time taken for this product to be made will determine the speed. So if there will be more of the products that will be made in a shorter time, then we can say that we have got a higher rate of reaction. But then when you are using your curriculum, how do you define the rate of reaction? The rate of reaction, it is the change in the concentration of products or reactants per unit time. Don't mind that those words which I have highlighted with bold, it means that those are keywords. You need to involve them in your definition. It is the change in concentration, 1 mark, of products or reactants per unit time. It makes 2 marks. So it is just measuring how much products or how many reactants are used up per unit time. So time plays a huge factor in the rate of reactions because you are measuring how fast a reaction is taking place. So in chemical reactions, when we are studying the rates of reaction, we talk of this this thing of effective collisions. So you need to understand, what do we mean when we are saying that we've got an effective collisions. So in chemical reactions we study every day, we consider the rates of reaction based on the number of effective collisions per unit time. So when we are saying that we've got an effective collision, it means we've got a reactant and another reactant mixing up together to form a certain product. Just like in this diagram here, we've got sodium mixing up with chlorine to make table salt, which is sodium chloride. So a collision is considered effective when these two reactants combine successfully to make a product. So effective collisions just means that two chemicals are bumping into each other, or they are colliding into each other, and when they collide into each other, they combine to form a certain product. So what makes those two chemicals to collide effectively? There are certain factors that contribute to the effective collisions. So for a collision to be effective, the reacting particles must have enough kinetic energy. So when we are talking about kinetic energy, remember we are referring to the energy of the reacting particles due to its motion. So the energy that this chemical has, for example, it is 45 joules, and then the energy that this chemical has, the one painted in red, it is 87 joules. So this is the energy that these two particles have. It is called their kinetic energy. So this kinetic energy has to be enough so that this reaction takes place. So it must be enough. When I'm saying that the kinetic energy is enough, it means that it is greater, or it is equal to the activation energy. Remember, the activation energy is the minimum energy required for a reaction to take place, right? For example, for this reaction to take place here, let us say that the minimum energy required is 100 joules. So it means that these two reactants, they must make an energy of 100 joules so that this reaction takes place. But then if the kinetic energy of these particles is lower than 100 joules, then it means that this collision will not be an effective one. Hence we say that for a collision to be effective or successful, it means that these reacting particles must have enough kinetic energy so that they can bump into each other effectively and form a certain product. And another second factor is the orientation of the chemicals. So it is the chemical orientation. So when chemicals are reacting in a certain orientation, they can make a certain product. For example, let us look at this first example. We've got this chemical 1, which is reacting with this chemical 2. So you can see that their shape here is complementary to each other in such a way that they can form a product. So it means this part is just going to join in with this part and they will successfully form a product. So it means that these have got a correct orientation. So if they've got a correct orientation, they will have an effective collision. But then if you look at this reaction number 2, this red particle, this part of it and this part of this other red particle, they will not be able to collide effectively. Hence, there will not be any product that was not formed. Hence, we say that the collision was not effective. So for a collision to be effective, the basic is that they must have the same shape, or they must be in the same orientation so that they can collide effectively. So here you can see even in reaction 3, when these parts bump into each other, they will not be able to form any product. But then in the first example, when these two parts bump into each other, they are complementary to one another in such a way that they can form a certain product. So using these 3 other reactions, which is 2, 3, and 4, there is no product that is formed. Hence, we say that the collision is not effective. So if those conditions are not satisfied, remember the first conditions was the kinetic energy, and the second condition was the orientation. So if those 2 conditions are not satisfied, then we will not have a effective collision. So for an effective collisions, we must have enough kinetic energy and the chemicals must be in the correct orientation. So if those conditions are satisfied, then boom, we have got an effective collision. So remember, an effective collision just means 2 reactants combine successfully or collide successfully to form a certain product. So if they don't have enough kinetic energy, they won't be able to combine successfully, or if they are not in the correct orientation, they won't be able to combine successfully. So there won't be any product formed. So if there are more effective collisions per unit time, it means that there will be a higher reaction rate. Remember that the whole point of a chemical equation is the formation of products. So here, if there will be more effective collisions, then there will be what? There will be a higher reaction rate because there will be more products formed. Remember, from the definition of reaction rate, we say it is the change in concentration of products or reactants per unit time. So if there will be more effective collisions, it means that there will be more products formed, or there will be more reactants that are used to form products. So this means that more particles are colliding successfully to form more products in a shorter time. So let us look at the factors that influence the collisions, and those factors eventually will influence the reaction rates, right? So we have got 4 factors that influence the collisions. So the first one, it is the temperature. We have got the concentration of reactants, the presence of a catalyst, as well as the surface area. So let us look at how these influence the reaction rate, or how do they affect the reaction rate. So let us first look at temperature. So when you increase the temperature of a system or the temperature of a chemical reaction, you increase the kinetic energy of the reacting particles. So remember that temperature, from the grade 11 definition, it is the measure of the average kinetic energy. So it means, for example, this is a chemical reaction taking place and we have got 2 particles and they're colliding with each other. So when you're going to increase the temperature here, let us say you increase the temperature to something like 50 degrees Celsius, it means that you are increasing the kinetic energy of the particles. So if more particles will have enough kinetic energy, then there will be more effective collisions. Because remember that for you to have effective collisions, then you must have what? You must have enough kinetic energy. So when you increase the temperature, you are giving these reacting particles the energy to collide with each other successfully or effectively. Hence, we say that when you increase the temperature, you also increase the reaction rate. So if they ask you this question, it will be 4 marks. They will say use the collision theory to explain how does an increase in temperature affect the reaction rate. So here you have to mention that increase in temperature increases the kinetic energy of the reacting particles. That's 1 mark. And then you have to mention that more reactants will now have enough kinetic energy because you have increased the temperature, right? That's the 2nd mark. And then if you increase, if more particles have got enough kinetic energy, then there will be more effective collisions taking place per unit time. Do not miss out this phrase per unit time. It is important. That's your 3rd mark. And then the last mark, the reaction rate will increase. So that is usually 4 marks. This is how you explain the effect of increasing the temperature on the reaction rate. If they say the effect of decreasing the temperature on reaction rate, you just do the opposite. You say that when you decrease the temperature, you decrease the kinetic energy of the reacting particles, then there will be less reactants with enough kinetic energy, then there will be less effective collisions. Eventually the reaction rate will decrease. So the opposite is true for this one. So let us look at the second factor that is affecting the reaction rate. So the second factor is the concentration of reactants. So when you increase the concentration of reacting particles, there will be more reacting particles available with enough kinetic energy for the reaction to take place, and there will be more effective collisions that will take place. Eventually reaction rate will increase. So let me explain this. So for example, here you've got a basin which I'm drawing here. Here is a basin. Let us just say here you put these 3 particles to react with each other. So when they react with each other, they will form a certain amount of product. Let us just say this one does not have enough kinetic energy. So it means that these 2 only will react. Hence, we'll have these 2 reacting with each other, but then this one did not react. What if you increase the concentration of reactants? Remember, the concentration of reactants, it is the amount of reactions present. So here, if we take another basin and we put more reactants, it means we are increasing the concentration of reactants, right? So let us just say these 2, this one and this one, they do not have enough kinetic energy. So it means these ones only will not react, but then the rest of them will react. So if we can look at the products formed here, this one, there will be more products that will be formed. But then these ones did not react. So you can see that if you increase the number of particles, which is the concentration of the reactants, then there will be more reactants that are willing to react with each other, that they will have enough kinetic energy, and then there will be more effective collisions that will take per unit time. So each and every one of these points is 1 mark each. It's 1 mark each, which completes 4 marks. So the opposite is true when you decrease the concentration of the reactants. So when you're decreasing the concentration of the reactants here, it means that there will be what? There will be less reactants with enough kinetic energy, then there will be less effective collisions, hence the reaction rate will decrease. Then the third factor that is affecting the reaction rate is the presence of a catalyst. So what is a catalyst? So a catalyst is just a chemical that increases the reaction rate without being used up. So basically a catalyst, it is something that makes a process faster. Yeah, that makes a reaction faster. For example, if you take, let us just say you are using firewood to warm up. You are using firewood to warm up water here, and then you are using an electric kettle to warm up water. Which one will be faster? It is the electric kettle than the firewood. So the electric kettle is more of a catalyst because it is increasing the reaction rate as compared to this one with firewood. So basically a catalyst is that chemical that you're gonna use to increase the rate of a reaction without itself being used up. So when you add a catalyst, then the activation energy will be lower, or it will decrease. Remember, we say that for an effective collision, the particles must have enough kinetic energy such that that kinetic energy is greater than the activation energy. For example, a reaction requires 20 joules, and we have got two particles. Another one has got 10 joules, another one has got 3 joules. So these particles cannot complete this reaction because they do not have enough kinetic energy, right? Because the kinetic energy that they have is lower than the activation energy, hence they won't be able to complete this reaction. But then when you are going to add a catalyst, this activation energy or the activation required will be lowered. So for example, this activation energy will be something like let's just say 12 joules. So it means that for this reaction to complete in the presence of a catalyst, it will need 12 joules. So this one with 10 and 3 joules, they will be able to complete this reaction because it has got lower activation energy. If you add these energies, will be what? 18 joules, of which 13 joules is greater than 12 joules in such a way that these can complete this reaction. So the whole point is here that when you add a catalyst, the activation energy will be lower. That's the first mark. And then what does that mean when the activation energy is lower? It means that there will be more particles that will have enough kinetic energy for the reaction to take place. That's the second mark. And if more particles have got enough kinetic energy, then there will be more effective collisions taking place per unit time. That's your third mark. And your last mark is the reaction rate will increase because there will be more effective collisions, meaning that there will be more products formed per unit time. So here, this is also 4 marks. So the last factor that is affecting the reaction rate, it is the surface area or the state of division. So surface area is just referring to the area occupied by the reactant. So you can just say it is the size or the area occupied by the reactant. So a solid reactant can be in a granular state or in a powdered state. So here I've used 2 diagrams to represent the surface area. So you can see that this is sugar, and then this sugar is in form of cubes. So it has got what? It occupies a smaller surface area. As compared to this one, this is granulated sugar or this is powdered sugar. You can see that it is occupying a larger surface area. So how does the surface area of the reactant or of the solid reactant affect the reaction rate? So let us look at it. So when we increase the surface area of the solid reactant, so how do we increase the surface area? Remember, it is just the idea that we crush this sugar and we make it more of a powdered sugar. So when we make it more of a powdered sugar, then it will have a larger surface area. So when we increase the surface area of the solid, that's the first mark, what will happen? There will be more particles that will react with the correct orientation. So here, at this point, if you take this block of sugar and you put it inside water, it will not dissolve easily. But then if you take this powdered sugar and you put it in the in a cup of water, it will dissolve easily. So it means it reacts quickly with water. So why does this one react quickly with water? It is because it is powdered. Right, it has got a larger surface area, so it means more of these particles will react with the correct orientation. But then if you take this one, which is in cubes, and you put it inside water, it will not easily dissolve. It will not easily react with the water. So when you're increasing the surface area, there will be more particles with the correct orientation. And then if they remember that the condition for effective collision is the kinetic energy as well as the correct orientation. So if there will be more particles with correct orientation, then there will be more effective collisions per unit time, and eventually the reaction rate increases. So when you increase the surface area, or you are making the reactant to be more of a powder, then the reaction rate will also increase. That is also 4 marks. So this easy example which I've made is that the cube sugar will take long to dissolve in water than the powdered sugar. Hence, most of the times you use soft sugar in your homes, you do not use the cube sugar. So that is the whole point. So ladies and gentlemen, thank you for watching this video. Please do mind that the way that they will ask this question, they will say use the collision theory to explain this and this and that. So the whole thing of collision theory, it is just understanding the concept of effective collisions and the factors that affect it. Thank you for watching. Don't forget to subscribe, tell your friends to stay tuned. Cut. And when the